Okay, welcome back. Today we're jumping into 4.1 Polynomial Functions and Models. It's going to be a little bit longer one, but the concepts should not be that hard. It's just we have a bunch of things to cover here. So we're kind of setting up this whole polynomial idea. And in the first unit, the first section, we're splitting it up into two parts. And the big idea here is we want to be able to identify polynomial functions, and then being given polynomial functions, we kind of want to know what they look like. So if we were to graph them, what are the characteristics of this graph, without maybe having to actually graph the functions themselves. So what polynomial functions are, they're made up of terms, right? So a bunch of terms of multiplying integers and variables with addition or subtraction in between. So you might see it in a textbook look like this. And one of the things about math and the notation of it is it's very confusing. And if you don't understand how each of the parts works, or like why it's so complicated, you can get really messed up for a while. But all this is saying is that each of these things here is a term. So you can have any amount of terms. Notice the dots in the middle. So it can be of any length. But what we need to make sure is that we have a number. Each of these variables represents an integer, right? An integer. And then each of the parts has a variable with an exponent. So n being the largest exponent, and that would be the degree, right? So the degree of a polynomial is the largest exponent. Usually when we write it highest exponent to the least exponent, usually here with an exponent of 0, which is just a constant. Okay, so the first example says determine if the following are polynomial functions. For those that are, determine the degree. All right, so here we have a 2, which is a number. That's cool. That's a term. We have a minus, right, in between, which is acceptable. And then we have 3x to the 4th power, which is also a polynomial. We know that because there's a number, which is 3. And we have a variable with an exponent, which is 4. So this is a polynomial. And the degree, right? So the degree says the highest exponent. So degree 4. Degree 4. Okay, for part 2, it's saying that g of x is equal to square root of x. So the thing that we're looking at here is a square root, right? So this is definitely not an exponent function. We don't have a whole number exponent. Well, we could change it to an exponent, but that's like for later down the road. But this one is a no. We don't do square roots. Square roots, any roots make it become not a polynomial. Okay, so for h of x, we have x squared minus 1 over x cubed minus 2. Now this one is very apparent because we have a division here, right? So this is going to be a no. Division is not included in our polynomial definition. So therefore, anytime we divide, this is not going to be a polynomial. Okay, f of x equals 0. This is a yes. Oddly enough, there's no degree to this, so we're not going to say the degree. They're saying anytime we have a 0, there's no degree. But it is just a constant, right? Anytime we have a number, like you'll see in the next one, that is a polynomial function. It doesn't have to have a variable on it. So let's look at number 5 now. G of x equals 8. Yep, 8 is an integer. It doesn't necessarily need a variable on it. So this is a yes. And the degree here would be 0. And the reason why the degree is 0 is because if we had 8x to the 0 power, that's the same thing as 8, right? Anything to the 0 power is 1. So therefore, this is degree 0. The highest exponent would be 0. Okay, now the last one's a little bit tricky because we have some multiplications in here. It doesn't quite look like a polynomial function because we have one thing multiplied by another thing. But the thing to remember is here that if we multiplied this thing out, x minus 1 squared, right? So let's do that. And I'm going to do it from my brain, but really we're just doing x minus 1 times itself, right? And we're doing the whole FOIL thing or distributive property to each part. But what we end up with is x squared minus 2x plus 1. And then if we distributed this now, 2x cubed, then we get negative 2x to the 5th plus 4x to the 4th minus 2x cubed. Now we definitely have a polynomial, right? Because this term is okay. It's a number with a variable with an exponent. Then we have addition, and then we have another number with a variable with an exponent. Then we have a subtraction with a number and a variable and an exponent. So this is definitely a yes for a polynomial. And then the highest exponent here is 5, so the degree would be 5. Whoops, that's kind of gross. Let's write that nicer. There we go. Now, the easier way to do it, if you kind of look at it, is that when we do our parentheses with the x plus or minus anything, we take that exponent on an x, so that would be x squared, right? And then we have x cubed. So if we add x squared with x cubed, well, multiply x squared with x cubed, we'd add the exponents, and then we'd get x to the 5th. It's just a little hint there that you can do it that way if it's easier for you. Okay, so this is when we kind of start talking about how the graph looks. So find the polynomial of degree 3 whose zeros are negative 3, 2, and 5. So this is very simple. So we're going to put 3 parentheses in here, and each of them is going to represent one of the zeros. So the first zero we're looking at is x minus negative 3. So what we're asking ourselves is, what would this look like if we plug in negative 3 for the x? What would make that 0? So that would be 3, and we know that because negative 3 plus 3 is equal to 0. Okay, then we move on to the next one, x. And then we're asking ourselves, for our x, if our x is 2, what minus that is going to equal to 0? That's going to be negative 2, because 2 minus 2 is equal to 0. And then lastly, we're looking at the 5. So we're looking at, all right, what would x be so that if we have our 5 there, it'd be equal to 0. So 5 minus 5 equals 0. So that's our third parentheses. All right, so if we make that equal to 0, then we know that if we say that negative 3 plus 3 is equal to 0, that's going to be 0. 2 minus 2 is 0. And then 5 minus 5 is 0. So we have all our 3 parts, and we're done. Now, the interesting thing here is, right, so it says find a polynomial degree 3 whose zeros are negative 3, 2, and 5. So let's look at the graph of this. So we'll go to Desmos here. Just so we can graph it and verify that what we're saying is true from our equation. So let's say that y equals, okay, and then we said that we had, just go back here, 3, negative 2, negative 5. Okay, so minus 3, or positive 3, plus 3, x minus 2, x minus 5. Okay, and then if we look at here, we can definitely see the graph of that has 3 zeros, and they're exactly where we want them, at negative 3, at positive 2, and at positive 5. All right, so just using that to verify that our equation is correct. Okay, this one is asking us find the multiplicity. Right, so the multiplicity is for each of these zeros, right, in parentheses, what is the exponent on it? So the multiplicity means the exponent. Okay, so for x minus 2, that would be, there's no exponent there, so it's going to be a 1. X plus 3, so let's just, x minus 2 is 1. X plus 3 is 2. X minus half is 4. Now what we're going to do is we're going to identify the zeros, right? So the 0 here would be 2, right? Because 2 minus 2 is 0. It would be negative 3 for the next one because negative 3 plus 3 is 0. And then it would be 1/2 for the last one because 1/2 minus 1/2 is 0. So what we're going to do is we're going to graph this. We're going to check the zeros again, but then we're going to see how the multiplicity affects our graph. So let's kind of write this down. This is a lot. So 5x minus 2, x plus 3 squared, x minus half to the 4th. All right, let's go back to Desmos here. So y equals 5. We have x minus 2, x plus 3 squared, and then x minus 1/2 to the 4th. Okay, so let's look at the negative 3 first. So negative 3 is squared, right? So if you look at it here, it's kind of hard to see because it's so narrow at that point. But what happens is it comes from the left side, it goes all the way up to the x-axis, it hits negative 3 here, but then it bounces back down. Okay, let's look at what happens at 1/2. So this one comes from the left side, comes up to the x-axis, hits it, and then bounces back as well. So notice that the ones with the even exponents, 2 and 4, bounce. Now let's look at what happens at positive 2. Well, this one comes from the negative side, goes all the way through the x-axis, and continues upward. All right, so what we want to note here is that for our multiplicity, if we have an even, that means it's going to bounce off the x-axis. So whatever direction it's coming from is going to hit the x-axis and go back in that same direction. And then odd, pass through. Which is kind of interesting. It's kind of neat, kind of interesting. All right, so this one, it's just asking you to find the multiplicity. But I figured that while we're at it, we might as well talk about why multiplicity is important. Because if it's not important, then why would we even attempt to do it? All right, so let's look at this next function. So f of x equals x plus 1 squared, x minus 2. So what we're doing here is we're trying to analyze this. We're trying to build up what this graph looks like. So find all intercepts for the first thing. So let's find the x-intercepts first. The zeros, those are easy. So what plus 1 is 0? Well, that's negative 1. What minus 2 is 0? That's 2. Right? So we have 2 zeros here. The y-intercept is also easy. The y-intercept, remember from Algebra 1, is the f of 0. So that means we're plugging in zeros here. So 0 plus 1 is 1. Oops. So we're plugging in our zeros. 0 plus 1 is 1. 1 squared is 1. 0 minus 2 is negative 2. So 1 times negative 2 is negative 2. So we found our x and y intercepts. Now we can go ahead and graph it. I guess we can probably just go ahead and use Desmos. X plus 1 squared, x minus 2. Okay, so x plus 1 squared, x minus 2. Okay, so if we kind of like zoom this out so we can see it, then definitely yes, we have a 0 there at 2. We have a 0 there at -1. And then note again, because right, the x plus 1, the 0 is -1. Because our exponent is an even exponent, it bounces at that point. Because x minus 2, the 0 is 2 there, 2 minus 2 is 0. And the exponent is technically 1, right, which is an odd, it passes through at that point. All right, so which leads us into the next question, right? So we graphed it, determine multiplicity. So multiplicity for our -1 is 2, right? It's an even. We saw that it bounced at -1. And then for our 0 at 2, that's an odd, that's 1. It passed through. Okay, so that's pretty much it for today. We're continuing this next time, but we just wanted to get you kind of comfortable in being able to take different parts of the polynomial function and understanding